In this first example, we're going to consider different ways to program Newton's method of solving a nonlinear equation, which in general can be written as trying to find the zero of some function which is too complicated to solve analytically. So if you imagine plotting the function f of x, then you'd have some root x naught, and the idea of Newton's method is to make a guess at the root. For example, to guess that the root was here, which is close but not quite right, and then to approximate the function as if it were strictly linear with the same slope and value that it actually has at this point, and then to use that to construct a better guess, and then to use that point in turn to construct a better guess still, and so forth. So that if the function looked like that, then the next guess would be as I just constructed here, and then we would go down here and say, okay, the new slope is right there, and then this gets to be hard to draw because I'm getting quite close to the root, but the slope takes me someplace right here, and then the next guess is up there, and I sort of oscillate around the final value here. Now, to turn that into a mathematical expression, what we say is that f of x is approximated as a first-order Taylor series around the initial guess x naught, which looks like this, and then we're neglecting all the higher-order terms in that expansion, which the first of which would be something like this. So if we ignore that, then this equation is simple enough to solve. Setting f of x equal to 0, we would then get, being able to solve for x here, we would get that x was x naught minus the function value at x naught divided by the derivative at x naught. And so then this expression here is how we take a step. So this is the recipe, if you want, for a single improvement of our initial guess. And so the procedure of Newton's method is to use that expression iteratively. That is, you have an x naught, it produces an x1 by this relationship, which you use over here, which produces an x2, and so forth. So you get a sequence of improved values like so, and eventually you either get tired of doing this, or the values become the same to within some precision, and then you stop. And so that's Newton's method. So having described this, we're now going to show how to code this in various ways using Mathematica, and along the way to demonstrate different styles of programming. As you'll see, procedural programming, which is the common approach in languages like Fortran and C, and functional programming, which is a more compact way of doing things in Mathematica. So here we are in Mathematica, and now we're going to, as I say, program Newton's method. And the first step is to write a function which takes that single improvement step, and that improvement step needs an initial guess and the function itself as input. So we define something called Newton's step, which is a function of the function f and the initial guess x naught, and it takes the form as I wrote it on the previous page, just like that. And now, in order to use this for something, we need to define a function that we want to try to find the root of. So let's define a function f of x is 4x minus e to the x, and just to plot that so we can see what we're doing, we see that actually it's going to have more than one root. Depending on where we take our initial guess, we're going to converge to this root over there or to that root over here. So, for instance, if we take a Newton step starting at the value of, I don't know, 0.9, then we get a value a lot closer to 0, someplace over here. You can kind of see that if you took a slope right there, you're going to land over here someplace. And now we need to figure out how to iterate this thing, because we want to use that as the next guess. And it would be a nuisance if we had to type by hand the old value into the thing every single time. That's not how we would want to do it. So there are various approaches we could use. An approach that looks a lot like what you would do in Fortran or C would be to make yourself an array of answers, a list of, basically a list of places to put the answers if you want to store sort of the intermediate answers. So if we want to store 5 intermediate answers, we might do it like this. And then to define your initial guess like that. And then to use a do loop, which would look like this. Do ants sub I, remember 2 brackets is how you access the ith element in Mathematica, is equal to x, and then update x with Newton step, like that, and then iterate this as I goes from 1 to 5. And then if we dump out ants at the end of this, we'll find that it's a list of progressively improved values, and you can see from the graph up here that the root is right around 0.36 something. So that's how you would do it if you were accustomed to programming in Fortran or C. This is a bit awkward when you consider the possibilities in Mathematica, and so let me sort of refine this version a little bit. One thing that's awkward here is that you've had to explicitly define a place to store the answers and access the ith element and so on. So a slightly slicker way to do that, but still procedural, that is using steps and a do loop and so forth, would be to make use of the list handling capabilities of Mathematica. So instead of defining ants to be a list of predefined length, we can always stick things onto the end of an existing list. So we start out with the initial guess as the first element of the list, and then we do the very same thing we did before. X is Newton step of fx, and then what we're going to do is to say ants is append of ants x, and what that append does is it makes a new list with x on the end of the old one. And now I don't need to mention I anymore because I'm just sticking things on the end of the list, and so then I can just say, well, do that 5 times and show me ants, and that works exactly the same. Doing it 5 times here is equivalent to 6 times up there because we start out with the initial guess in there. So this is 5 iterations. And that's a little cleaner. I don't need to talk about the ith element and so forth, but there's actually much nicer ways of doing it than that. For instance, we can use table to generate ants directly, like this. Table of x equals Newton step of f and x, and we want, say, 5 things in the table. So what is this going to be a table of? Well, this statement in here gets executed and its output is going to be x. So the table won't have the 0.9 in there, but it'll be a table of the next values that we generate, and you'll see that that doesn't require any ands or appending or anything like that. You just get, there they are, the 5 values following the initial guess. So that's nicer still. We don't even have to make reference to some place that we store things. We just build the table that we want. Okay. But there are fancier things still that we can do, which are heading more in the direction of functional programming. For example, there's a function called nest list. And if you ask what nest list is, it's a little complicated. It gives a list of the results of applying a function to an expression 0 through n times. And to understand what that really means, you can apply it to something that doesn't have any predefined meaning. And so you can see that if I nest list the function foo onto the value a 3 times, what I get is a, foo of a, foo of foo of a, foo of foo of foo of a. So you see, this is just perfect for iterating. So if I, what I want to do is nest list a function which takes x naught to being x naught improved by 1 step. And I can do that in the following way. I need a function which is only of 1 argument, which I can apply to my x. And Newton's step isn't quite like that. So I use another little feature in Mathematica, which is to define an on-the-fly function. I'll talk about this in just a minute. So this on-the-fly function here is a function that you can tell by the ampersand at the end. Its argument is the number sign, and this is its definition. So we just stick the f in there because we know we want that, and then the whole thing is just a function of whatever the argument is. And now this nest list will provide me with the iterates in one go. And I can even go a little slicker than that because we don't know how many iterations we need to take in order to stop. And so there's an additional function called fixed point in Mathematica, which does an iteration like this repeatedly until the result no longer changes. And so if I say fixed point of Newton's step of f and its argument applied to 0.9 as the starting point, then I just get the final value. And that is an example, the nest list and the fixed point and so forth, of functional programming as opposed to procedural programming. You don't tell Mathematica what to do in terms of the do loop. You use its own recursion and iteration functions to get the lists and answers that you want.